Hi, and welcome to the Simulation Step Up series. My name is Ramesh Lakshmipathy, and I'm a Senior Technical Sales Specialist with Dassault Systems SolidWorks Corporation. Now, in this presentation, we'll review some of the connectors in SolidWorks simulation. So let's get started. So why connectors in the first place? Well, connectors connect two or more parts of the assemblies together. They transfer loads between the connected parts. They can resist and take on preloads as well as external loads. In SolidWorks simulation, there's a wide variety of connectors to select and use from, such as springs, pin, bolt, bearing connectors, spot welds, edge welds, links, and rigid connection. Now, all these connectors are virtual, meaning there is no physical geometry required for simulation. Hence, there is no stress calculations available. However, the connectors do report some load results that can help with sizing requirement, such as the axial shear forces, bending moment, and torque. In this presentation, we'll talk about springs, rigid connectors, links, spot weld connectors, bearing connectors, and finally, edge weld connectors. Keep in mind there is a separate presentation on bolt connectors as well as pin connectors as part of the simulation step-up series. So I would recommend that you watch those presentations as well in addition to this particular presentation. Let's start with spring connectors. Well, spring connectors essentially connect or represent the springs in your model. There are three types supported. The first one is the general purpose tension/compression, which generates a force as soon as the parts start to move. Next is the compression only springs that can be used for rubber bumpers or springs that aren't attached but provide a compressive interface when sandwiched between two different parts. And finally, there is a tension-only spring option that can be used to model cables or ropes that cannot take on a compression load, but in tension can drastically alter the stiffness of the system. Here are the geometry selections. Flat parallel faces are the most commonly used geometry selection for springs, and we'll discuss this later. It is really in the best interest to make sure the selected faces are not only flat and parallel, but that you also have a split line, usually the diameter of a spring, defining an area of contact for that spring and which is identically projected on both faces. Now, if these split line patches are improperly aligned, you can actually run the risk of introducing a moment in your model that was not intended. The concentric cylindrical faces option is not a torsional spring. It has limited use, and we'll discuss this in a few slides. And finally, the two locations option is helpful if you're trying to apply soft springs manually to stabilize the model instead of using the soft spring option in the study properties. Now, as part of the spring connector definition, you can also specify the spring stiffness as a total value or a stiffness that is distributed over an area. You can control or input values for the normal as well as the shear stiffness and also provide a preload if required for the spring. Now, these are pretty self-explanatory, but the distributed versus the total stiffness choice warrants a little bit more discussion. Now, when using flat parallel faces, the most important thing to note is the common area of projection between the selected faces for the spring connector. As illustrated here, the program prefers to project the smaller area onto the larger area. And so usually the smaller area should be selected as the source face in the spring connector definition as shown here. Now regarding the stiffness options, if the source face is completely projectable within the target face, the total stiffness values can be used. If not, the distributed option should be used. Now in the example shown here, if the opposing circular patches were misaligned, you could set your spring up with the distributed stiffness, but a moment would be introduced in the model because the line of action between the faces through the spring is not perpendicular to the parallel faces. This effect could be small, but it could alter your interpretation of the load path. So bottom line is watch out for unexpected moments while using the spring connector. The concentric cylinder option was implemented for a very specific purpose, but that is now addressed with the journal bearing connector. It is meant to automate a more traditional analysis technique where the contact is approximated between the cylinders with springs versus using an actual no penetration contact condition as shown in this particular image. Now keep in mind that this concentric cylinder option is not for simply connecting a set of cylindrical through holes as illustrated in this particular image. Let's move on to the rigid connector. The rigid connector ties two faces together rigidly. The word is intentionally emphasized since rigid really means rigid. It can be used as a means to constrain any undesirable rigid body motion as long as the place where the applied rigid connector is that's of no interest to us. Now keep in mind this is not identical to a bonded contact, which does allow some local bending between the bonded faces. The faces attached rigidly will never change shape or change orientation with respect to each other. So use this connector as required because if misapplied, it can actually greatly overstiffen your model and render some unanticipated results. The link connector is another highly idealized connector. Like the rigid connector, it ties the distance of the vertices to each other rigidly, but does allow for some local rotations at the end of the link, much like a connection through a ball joint. This is also, we can say, an equivalent of a very high stiff vertex to vertex type spring connection. So again, while less rigid than the rigid connector, the link connector should only be used if you truly understand the effect of it having on your model. In this example shown, comparison is done between using a rigid connector versus using a link connector on the same problem. And you can clearly see the additional moment applied to the faces in the link connector example is obviously based on the bending of the structure. Now, probing the displacement plot at the two nodal attachment points of the link connector clearly shows that the distance remains unchanged after deformation. However, there is a bending or rotational effect that can be seen due to the y coordinate being different after deformation. Spot welds connect two or more thin overlapping metal sheets at small areas called spots without using any filling material. The spot weld connector allows you to quickly define multiple spot weld connections between parallel faces of two different parts, and these parts do need to be close to each other. Now you can define a spot weld between a solid to solid, solid to shell, and a shell to shell geometry faces. Spot welds requires vertices or reference points for the spot weld location, and you can also input a spot weld diameter as well. The important thing to understand is a no penetration contact needs to be defined between the two faces, especially if you suspect they might come into contact during the deformation process. In shells, if you have modeled adjacent thin walls as mid-plane shells, keep in mind that there is going to be a gap of half the sum of the wall thicknesses. The no penetration contact does account for the shell thicknesses, but it's absolutely important to ensure that the shell offset is correctly defined. And lastly, behind the scenes, a spot weld connector is modeled as a beam element that is shear flexible. So an important aspect of the spot weld is the node near the attachment vertex. Based on the diameter specified, that node is tied up to the spot weld element. So if the mesh is really coarse, this could result in some local stress concentration effects as illustrated in this particular picture. The results away from the joint are probably okay, and usually 1 to 2 spot weld diameter away, the results are generally acceptable. The recommendation is also to set up correctly positioned split line patches, meaning create circular patches on the connected surfaces using the spot weld diameter. An upside to this is that this free body force is available for that split line phase will give you important feedback on the loading through the weld. So a spot weld doesn't force a node at the reference point, and the user has no control over how many or which nodes get used. Let's take a look at this example where 9 spot welds tie up a three-sided part to a form floor. As shown, if the mesh is really very coarse, the spot weld will actually grab the closest node, and that node may not be close to the actual spot weld location. So this model is solved with a default coarse mesh as well as a refined mesh on the surfaces where the spot welds are attached. The fine mesh does take a little bit longer to solve, and some split lines could have reduced the number of smaller elements needed. Now you can clearly see the results from using a coarse mesh versus a fine mesh. The stress near the spot weld connection in the coarse mesh scenario are discontinuous and they don't look reasonable, whereas the results near the spot weld in the fine mesh look much more reasonable. While you don't need to refine such a large portion of the model, a combination of split lines and mesh refinement can greatly enhance the spot weld results. A bearing connector connects a cylindrical face of the shaft and housing, thus replacing the bearing part geometry. The intent of this connector is to provide a local flexibility that a bearing would allow while still restraining the shaft. Here, the housing is not much stiffer than the shaft, otherwise we can always use the bearing fixture instead. We'll talk a little bit more about the bearing fixture later on, but essentially with the bearing fixture, the housing is not modeled and the part is connected to a fictitious ground. The shaft faces must be split to represent the contact areas, and the shaft face also must be the first selected geometry in the bearing connector definition. Now, the allow self-alignment option provides an off-axis rotational degree of freedom as a ball bearing might see, meaning there is no restriction to bending deformation, or in other words, no moments develop at the shaft cylindrical face. Let's talk a little bit more about the self-alignment option. So the standard non-self-aligning bearing, which would typically correspond to a roller or a needle bearing. Here the bearing connector is represented using radial springs distributed radially around the shaft, which are projected from one surface of the shaft to the surface of the housing used in the bearing connector definition. Here is a screenshot of the results from using such a bearing option, clearly showing that there is no off-axis rotation around the bearing area. On the other hand, a self-aligning bearing allows off-axis rotation of the shaft, and this typically corresponds to a self-aligning ball bearing with two rows of balls and a common concave speared raceway in the outer ring. Now here the bearing connector is represented using a very short spring-like element that allows a stiffness to be provided in the axial and the lateral directions. Now the spring-like element is connected by rigid bars to the entire surface of the shaft you have selected, and also to the entire surface of the bearing housing face selected in the connector definition. And clearly here with this bearing connector, you can see the results show the off-axis rotation around the bearing surface. Now, the bearing stiffness option allows for some local compliance to be taken into account on the shaft. So, for example, the rigid option applies a very high stiffness value to the springs that are distributed radially between the selected cylindrical faces of the shaft and housing. The shaft face cannot translate laterally or axially using this particular option. On the other hand, the flexible option allows the selected shaft face to deform and axially displace. You can define total lateral and axial direction stiffness for a self-aligning bearing connector. For a no self-aligning bearing connector, you can actually define a distributed radial and axial stiffnesses as well. Now, to obtain numerical values for the bearing stiffness, you can always refer to the bearing manufacturer's catalog. And also keep in mind that in some of these catalogs, the term rigidity may be used instead of stiffness. Lastly, the stabilized shaft rotation option, it actually prevents any rotational instability caused by torsion that can lead to numerical singularities in the simulation. So behind the scenes, the simulation applies springs with low torsional stiffness to the shaft's cylindrical face that provide circumferential resistance against torsion. So this prevents the shaft from rotating freely about its axis and eliminates the instability. Now keep in mind that this option is not meant to prevent the relative rotation between the shaft and the housing so as to resist a significant torque. If you think about a shaft cantilever through a ball bearing, it has mostly unrestricted off-axis play until a certain angle is reached and the clearances are all taken up. At that point, the off-axis stiffness increases dramatically. Now, this can be approximated with the bilinear curve shown in red in the graph. Now, two other options are available prior to using the bearing connector. One is to fix the entire area that interacts with the bearing in a race shown by the green K line, which equals an infinite stiffness value. And this method is non-conservative as it stiffens the shaft unnaturally, and the stresses downstream will report a lower value than they should. On the other hand, you can use a remote load displacement option where the inner raised surface is tied up to a central point, and the central point can be restrained solely in translation so as to behave like a ball joint. And here the stiffness value is literally zero as shown by the blue horizontal line in the graph. So this technique works very well for small rotations when the interaction is on the K1 portion of the bilinear curve, but can also be overly conservative if the clearances are all removed and the bearing responds with the K2 stiffness. So the bearing connector, bottom line, provides a linear middle ground where by adjusting the single radial stiffness parameter, you can specify an average off-axis stiffness. Let's look at a couple of bearing connector options and compare the results with the remote load scenario. So in the first case, a roller bearing connector is applied to the shaft face. So the shaft is held pretty rigidly with this connector, more of like applying a fixed restraint on the shaft face. You can clearly see the maximum displacement is about 8 thousandths of an inch. In the second case of a ball bearing connection, shows a much larger displacement due to its off-axis rotational effects. And finally, in the third case, a remote load displacement restraint was applied at the geometric center of the bearing surface and allowed to rotate freely. And here the displacement clearly shows more or less the same response as the ball bearing. If you look at the stress distribution, with the roller bearing connector, the bending stress is not so dominant. So here the max stress can be expected to be much smaller. Compared to using a ball bearing connector, you can clearly see that the bending stress for the same problem is much more dominant, and here the max stress can be expected to be a lot higher. So this is in line with using a remote load displacement scenario where the bending stress again is dominant or more or less the similar response, shows a similar response as the ball bearing connector. So bottom line is, which option would you choose? If you know that your shaft rotation will take up the clearance on your bearings, determined from some simple testing, use a roller bearing connector. Otherwise, stay conservative and use a remote load displacement option. The ball bearing option doesn't buy you much over these two different methods. And finally, with the bearing connector, you have access to different types of results. So for example, you have access to the tabulated results for the bearing connector forces like the shear forces, axial forces, and the bending moments. And to get those results, you can right mouse click on results, go to list connector forces, and here's an example of what you might actually get in terms of those forces. So for a roller bearing connector, you can clearly see that there is a lot of bending moment reaction going on because of no off-axis alignment, or in other words, no off-axis rotation. The same in the case of ball bearings shows a zero value for bending moment because of the allowable rotations, and this is what we would expect. Now switching gears, let's talk a little bit about bearing fixtures. The bearing fixture can be used when the housing is much stiffer than the shaft. Essentially, you can eliminate the housing geometry, which helps simplify the simulation meshing and solve times. The good news is that the options here are exactly the same as the bearing connector, except for not having to select the housing cylindrical face. Now behind the scenes, the program uses rigid bars to connect the nodes on the bearing surface to the center point, and that center point is connected then to a global ground or a fictitious ground using a spring element, as illustrated here. Now, one thing with using bearing fixture is to get the reaction forces. So it's important to know that the total reaction force in the system includes the sum of the reaction forces of the applied fixtures plus the bearing fixture. In SOLIDWORKS simulation, the reaction force is only reported at the applied restraints and not on the bearing fixture. So let's take a look at an example of a shaft where the only fixtures holding the shaft in place are the bearing fixtures. So there's no other applied fixture in the system. Now to obtain the forces, we have to use the free body force option generated on the bearing surface. So to do this, before you run the simulation setup, make sure that in your study properties, the compute free body force is checked as shown here. Then after the simulation is run, you can access the results force dialog box, select the free body force option, Then select the bearing fixtures phase, click on Update, and get access to the bearing fixture reaction forces. The last connector we're going to talk about is the edge weld connector. Now this connector joins surface bodies together. It can be used to size and verify the goodness of the weld. Behind the scenes, the program extracts the loads and the stress information to calculate the appropriate weld size requirement. The weld types are really the first input in the edge weld connector definition. Here are the supported weld types. The groove weld is a weld applied in a preformed opening or groove between the two metal parts. And the groove welds defined can represent all edge-to-edge weld types like the square, butt, V, J, and U conditions as well. The fillet weld is a triangular weld that joins two metal parts at a right angle. In terms of the geometry selections, face set 1 should belong to the terminated part, and it could be a shell face or a sheet metal body. And face set 2 could be a shell, sheet metal, or a solid body. For fillet welds, the selected faces of sets 1 and sets 2 are perpendicular to each other. For groove welds, the selected faces are parallel. Now the program automatically detects the touching edges between the selected faces to apply for welding. Non-touching edges can also be selected in the definition, but they must actually belong to the terminated part. The weld sizing calculations uses the throat shear method. So really this is based on forces rather than stresses to size the weld. Behind the scenes, the program calculates the throat shear stresses based on the external loads and compares that to an allowed shear stress value. So this is more of a convention, not really reflective of the actual stress in the weld. For weld sizing, both American and European standards can be used to perform the weld size calculations. Now I'll talk a little bit about the American standard in this presentation, but more details and information on both these standards can be found in the online help. So with the American standard, the first step is to specify or select the electrode from a predefined list as shown, or it could be a custom steel or custom aluminum scenario as well. The weld strength is set to the electrode's ultimate shear strength value. The safety factor reduces the weld's ultimate shear strength value by a certain factor. And here you have three different choices. The first choice is the American National Standard for Automotive Lifts, where the weld's ultimate shear strength is reduced by a default factor of 3. The next option is the under the hook lifting devices, where the shear strength is reduced by a default factor of 5. And the third option is really a user input that can be custom defined. The estimated weld size lets the program calculate the appropriate size for the weld connector. So the program uses the specified value and compares that with the appropriate weld size calculated and displays the results in the weld check plot. We'll look at the weld check plot a little bit later. So again, the forces and the moments are calculated for all the mesh nodes on the intersecting edge of the terminated part. So behind the scenes, a local quantum system is created at each and every node as shown. All right, let's talk a little bit about behind the scenes calculations for the edge weld connector. The forces and the moments are calculated for all the mesh nodes on the intersecting edge of the terminated part. A local quantum system is created at each node as shown. The shear axial forces and the bending moments are then transformed into stress components per unit length. And then finally, the resultant stress is calculated and compared to the allowable to get the weld throat size and the weld size requirement. Once the simulation has been run, you have access to some key and fundamental results. One of them is the weld check plot. This is a visual feedback on safety status based on the calculated weld size. So the program right off the bat lets us know what connectors need attention, which means the estimated weld size is less than the calculated weld size on these connectors. The load capacity might be at risk, and you might want to consider resizing the connector. You can also list the weld results, such as weld size, throat size, joint forces, and bending moment. And plus, you can create an XY graph of the weld size versus the seam distance as shown here. Okay, so this chart summarizes all the connectors that we have discussed, and you can really use this as a reference going forward. So the first column is the study type, kind of gives us an idea of what connectors are supported for what study types. The next column is part or assembly, so letting us know what connector works at the part level, at the assembly level, or both. The mesh type column is self-explanatory, but again, you can utilize this as a nice reference as well. And finally, the geometric entities and the reference geometry column, they both give us a good idea as to, for each and every connector, what are the ideal or the most efficient geometry selections as well as reference geometry selections. In this presentation, we reviewed the remaining connector options such as springs, rigid connector, links, spot weld, bearing connector, and edge weld connector. We looked at some setup options for each one of these connectors, some do's and don'ts, and also finally we looked at what model type and study types can utilize each one of the connectors. So for more information, contact your local SOLIDWORKS reseller for an in-depth training or support on using connectors in your design work, or you can always review the online help for a more detailed description of the features discussed in this presentation. Thanks for listening and thanks for your time. I'll see you next time on another episode of the Simulation Step Up series. Have a great day. All right, that concludes this presentation. You can watch this presentation as well as several other presentations as part of the Simulation Step Up series on the Simulation YouTube channel. I'll see you next time. Thanks and have a great day.